Good afternoon, Anna, everyone. Okay, very good. Come to here. Good afternoon. Good afternoon. Mhm. Okay, good. All right. Yesterday, I think I just started the concept of internal force, if I'm not wrong. Yes, yes. And that internal force, initially we started calculating in massless free body diagram also. Very, very, very. Right? In continuation, we are coming to that concept. In massless string, what is the tension? And here, how to use the free body diagram. Okay, good. Come here, Nana. Today's class, suppose I take this is a support. Okay, and from the support, I am suspending one mass here. And then this is actually considered as massless string. String means the definition yesterday I told. It may be either rope or wire or thread. Okay, massless string. And then here you are suspending some load. Okay, either sphere or some block. Like this. Right? And considering its radius as or actually unnecessary data, this is. It is the radius but unnecessary. And its weight acts in what direction? All of you know. This is the direction of weight acting here. Sorry. This is weight, mg. So when an external force is there, immediately here some internal force is developed in the massless string in opposite direction. That is called as tension. Yesterday what I said. That tension here I am drawing. This is the tension in the string. Let it be T. Okay. If tension is mutual like action and reaction, the reaction other molecule, if I assume here at the point of suspension, then reactional force will act like this, what I said yesterday. That will be here like in the downward direction. Okay, this is also T. Till here, I think you don't have any doubts. If you have any doubts, you can ask now. Do you have any doubts here, Nana? Even in the tension concept or the external force concept, anywhere, no doubts. Okay. But keep in mind, in every problem, we have to assume two tensions in the string in opposite directions. Okay. So we are coming to here the free body diagram. This is suppose the first body if I consider. Okay. And this is our FBD free body diagram. Okay. In free body diagram, first we have to check whether the sphere is in motion or at rest. Okay. Motion or at rest means you only observe the sphere is appear to be at rest or in motion. You answer this question. In this case, it is at rest. Very good, very good. In this case, it is at rest. Right. So here in the free body diagram, first I'm checking that one, whether the mass, what is present in the free body diagram, whether it is at rest or in motion, first I check. Okay, means In all the cases, next in numericals also, you have to check the problem in the same way. That's what I'm saying. Okay. After drawing the free body diagram, you have to check that mass is whether at rest or in motion. Luckily, in my example, in this case, I got here the mass is, I observed that the mass is at rest. Here, the sphere is at rest. Sphere is at rest means, according to Newton's laws, net force on the body is equals to 0. Since it is at rest, Newton's first law. Okay, since the net force is equals to 0, the body at rest will be at rest. Okay, and then, sir, why you wrote net force, sir? Look at there. Two forces are acting in FBD here on the sphere, on the same sphere. One is internal force, other is external force. Two forces are acting here. But still it is at rest. Means net force I have to calculate or not? I have to calculate. Why? Because two are there, not single one. That two, they are in opposite direction. That's why can I write one upwards? Okay. Suppose that is T. If I take other is mg. Actually, I have to take plus, but they are in opposite direction. So I have to put minus. Net force is equals to 0. That you are telling in the string, Nana. T minus T equals to 0. Akhil, I am asking in this free body diagram I have drawn here. Okay. Means to understand, I will draw one more here, Nana. You can understand clearly. If I take this is the free body diagram, Mr. Akhil, then T minus T is equals to 0. Now you understood? Akhil Gollapudi. The second one I have drawn here. In that free body diagram, T opposite directions are, then net is equals to 0. Yes. Okay. But I took here free body diagram for the sphere. On that, I am writing the net force. Yeah. Net force on the sphere. One is upwards, other is downwards. So opposite direction, I took T plus minus G, that is T minus G is equals to 0. That implies I'm getting here T is equals to mg. Okay. So anyone, if you ask you what is the use of free body diagram, from the free body diagram we can calculate the net force including the internal force. That is the use. Okay. So I am writing here use of FBD in a system of many masses. Okay, many masses. It is easy to measure the net force acting on a single mass. Play the simple means single. That's why on a mass. Okay. So you have to understand that free body diagram we use only in a system for a single mass. Sir, there are suppose two masses, sir. Draw two free body diagrams. Sir, there are 10 masses, sir. Draw 10 free body diagrams. Now you understood, Nana? Free body diagram only for one mass. Okay, in a system. Yes. Okay. Sir, if there are three masses, sir, draw three free body diagrams. You can calculate on each mass what is the net force. Okay. Sir, more clearly you explain, sir. Okay, sure. Come to here. Suppose if I take one more example. I am writing. I am taking one more example here. I am taking the second example there. Example 2. Oh, here I am taking, suppose this is a smooth surface, and on the smooth surface I am placing two masses here, 1 and 2. Okay, different masses. Okay, that's why I mentioned with the different colors. Like this is suppose M1 and it is M2, two different masses. Okay, and here we consider the surface is smooth. There are no opposing forces from the surface. Happily, this is free surface. Okay, like well polished marble surface. Okay, smooth surface. And here those two masses are usually connected with one string here. Okay, no need to ask Nana. Initially, in all cases, every time I can't write it is a massless string. You consider that every time they are massless strings. If there is some mass to the string, I will mention. Okay, or Nana, there is a mass to the string. If I'm not mentioning the mass of the string, you have to consider that it is a massless string. Will you accept? I'm not giving any mass here. So, yes. So it is a massless string. Okay. But I'm not writing here. You have to accept that. Good. And then here, if I leave that string, it will slack and will fall like this in between the two masses. That is as a, like a string. So to stretch it straight, what I have to do, I have to apply some force on either blue color mass or red color mass. That only I told Mr. Aditya MS. Okay, not only in this case. Next, in all cases, we have to consider, you have to consider, unless until I tell there is a mass to the string. Okay, good. But every time I won't mention it is a massless string. Okay, you have give the permission to me that to consider it is a massless string. Good. With the kind permission from the HIMS, we are considering this as a massless string. Okay, and now I am applying some force here on the mass F1. Okay, this is external force. Yes, thank you. External force here. Okay, look at here, Nana, string is massless. So no need to take free body diagram for the string. So here two masses in this system. So I think you have understood a bit here. Oh, sorry, is going to draw two free body diagrams here in this problem. Okay, so I'm going to draw here two light colored free body diagrams. One for the first mass and two for the second mass. Okay, these are the free body diagrams. Okay, this is FBD of first mass and this is FBD of second mass. Okay, now check here, when I pull this mass towards right, in what direction the tension in the string at the first mass will be developed? Either it is towards right or left. Quickly respond. Right or left, the tension in the string. Amog, put 1. What is the 1? Right, left or 1? Left. Very good. So it will be towards left. So that tension here I am taking. Here the tension is towards left. Towards left. Yes, this is tension. Okay, good. Here, if I take the tension towards left, then at the other mass, in what direction I have to take the tension? Towards, good. Lakshmi Gayatri this time quickly responded. Right, good. So shall I draw towards right, Nana? Ishan? Okay, good. Towards right. Yes, yes, yes. This concept already we learned here in the first example. So here, this is the tension, massless string, same tension. Here we assume both must be in opposite direction, like action and reaction. Okay. And here I am saying that in this case, suppose the whole system, like engine is connected to one compartment of train. Here, when engine moves forward, the compartment moves backwards. The compartment, the box here also moves forward. So I think both will move forward with some acceleration, common acceleration for both. Okay, train is the best example. If engine moves with an acceleration of 10, all boxes here, compartments move with the same acceleration. Okay, here also we consider all the masses, means the two masses move with the same acceleration A. Okay, means indirectly I am saying that it is not only the massless string but also inextensible string like a rubber cord. Okay, not like rubber cord. Okay, rubber cord means right, rubber, if you suspend this one rubber thread, Nana, it will elongate, but the string is not elongating, inextensible, not elongating. Okay, that's why both move with the same acceleration. Okay, then you may ask, sir, if the string elongates like a spring, sir, spring also elongates, then that time confidently you say both the accelerations are not equal. Okay, so shall I write that point here as no? If the string is, yes, if the string is inextensible, then the accelerations of the masses are same or equal. Okay, next, if the string is extensible, in bracket like rubber or spring, okay, then here we say then the accelerations, confidently we say, okay, by beating our heart with the hand, okay, means with the palm, and straight away we say the accelerations are unequal, sir. Okay, right, this is the story, Nana. So initially I'm taking all the times inextensible and massless string. That's why every time I put acceleration same. Okay. Now look at here. The two masses are like in the first example, they are at rest or in motion. Nana, here the two masses. Are they in motion or at rest? Respond. Rest or motion? You assumed some acceleration there. So they are at rest or in motion. Anyone, please? Yes, Ammaya. At least one person responded. Ammaya, two persons responded. Thank you. Thank you. I think all of you are there in the fatigue stage. Okay, weekend effect, I think this is. Yes. Okay, because of weekend effect, I found very less response. No problem. Thank you. Anyway, here both are in motion. Okay, in motion, first body is in motion. What about the second one, Nana? Is it at rest or in motion? Second one, if engine moves, the bogies will be super. If engine moves, the bogies means here the compartments will be here in Hyderabad only. Only engine goes to Kakinada. Ishan. So both are in motion, not at rest. Okay, very good. So both are in motion, right? So both are in motion means that implies I have to write here. F net is not equals to, since they are in motion, not equal to 0, okay, on both the masses. Okay, that implies from FBD of 1, okay, I write here, I can't say F net equal not equals to 0 means I can't write like T minus mg is equals to 0. I have to write either T minus F is equals to F net or F minus T is equals to F net. Either T minus F or F minus T. Why? Because they are in opposite direction. Oh, Tanisha gave the answer here. Okay, very good, Nana. Right. Now, Tanisha here, T minus F is correct or F minus T is correct? Out of these two, only one is correct. Then which one is correct? First one or second one? F minus T. Very good, Lakshmi Gayatri. Why F minus T is correct, not T minus F? Yeah, Akhil Golapudi, yes, accepted. But F is greater. How can you say F is greater? Yes, you are right. You are correct. But very good. So the body moves. Very good, very good. You are getting the acceleration in the direction of F. Yes. You are getting the acceleration in the direction of F means F is greater, T is lesser. Okay. F is greater, T is lesser means I should not take T minus F. F is greater. So F minus T. Very good. So concluded here. So this is not T minus F. It should be F minus T. Yes. Okay. It is F minus T means F net already Newton gave the formula. If mass is constant, F net is equals to mass into acceleration. Okay. Here the mass is m1 into its acceleration common. Both move with same acceleration. A is equals to F minus T. Will I take it as first equation, Nana? This is first equation what I'm taking. M1 into A is equals to F minus T. Yes. Now come to from FBD of 2. Okay. Look at the second FBD, Nana. How many forces are acting there in the FBD in this box? Are you finding any two forces on both the sides? No. Very good. Lakshmi Gayatri, correct. Only one force is there. That is T. Only one is there. Yes. FBD, F net, only one is there. That equals to T. Okay. So F net again according to Newton's law is M into A. Mass in the second box is M2 into common acceleration is A only. No need to write A2. That is also A equals to T. Take it as second equation. Okay. I put here in a box and I take it as second equation. Right. Now it is the time to solve the two equations. Sir, you gave two equations means are there two unknowns? Yes. What are the two unknowns, sir? Tension is unknown, acceleration is unknown. Okay. Okay, no problem, Anna. Finish it. Okay. And here, first, I want acceleration, Anna. So shall I add the two equations, Anna? 1 plus 2. So I am moving to here 1 plus 2, equation 1 and equation 2. Right. If I add the two equations, if you see here, while adding, T get cancelled and right hand side you will get F and right hand side M1A plus M2A. So I write that part here, M1A plus M2A left hand side is equals to F after cancelling T and T. So I want acceleration unknown. That implies A is equals to F by M1 plus M2. First, wait for a while here. For what, sir? Look at. Try to extract one shortcut from this formula. What is the shortcut, sir? Look at here in the diagram. External force is there. Internal forces are also there. Okay, but finally resulting in the acceleration in the result, you observe any internal force is there in this equation, means any tension term is there? No. Okay, so can I write it as a shortcut? In a system, of course all masses are connected with massless strings. Okay, and inextensible conditions applied in a system of masses, if the net external force is F, number one, means I am taking this F as only external force, that to net external force. Okay, and is F, and the total mass in the system is sigma m. I think you know how to write sigma m. Since there are two masses m1 plus m2, three masses m1 plus m2 plus m3, four masses m1 plus m2 plus m3 plus m4, and so on. That can be written as sigma m. Is it right, Nana? Okay. Then the shortcut to find out the acceleration, A is equals to the net external force divided by the total mass in the system. Okay, it is a shortcut. Sir, you said the shortcut, but not. followed properly, sir. Okay. For a while, you give pause to this question and will you move to another question and there will you explain this shortcut, sir? Sure. Always the student's wish is the master's wish. So you ask, we explain. That's it. So here I am giving the respect to the student and moving to the next example, giving a pause to this pause, small pause. Take a pause here. Okay, and move to the next one. Example. Why? Because student asked. He did not follow this shortcut formula clearly at all. That's why we are moving to the next example. Okay, take this example. The student, Nana. The student. Are you not the student? Are you not my student? Respond. Okay, good. So student, one student asked. Here I am taking two masses. Okay, connected as usual with a massless string. And he only created some numerical values here. He took it as 3 kg at a. This is second mass 2 kg at a. Okay, and here wisely he applied one force towards right on the first mass, and here he applied another force on the second mass. Yes, yes, yes. Here this force is suppose 10 newtons. Okay, and this force is suppose 25 newtons. Okay, the question is, in the figure, of course, again we are following all the conditions, smooth, inextensible, massless. In the figure, find the acceleration, what he asked. Okay, this time I am preparing for objective test, so I have to solve a numerical quickly in a short time. That's why here I am not drawing FBD1, FBD2 equations, internal forces, two equations, solving them, and finally finding out A. I am not preparing for IP. I am preparing for not board exams, for objective. Then I need shortcuts. So using the shortcut here, SAR told A is equals to find out the net external force. Look at here, two external forces are there. Okay, so come to here, the solution. Two external forces. Out of these two, 25 is greater and it is in opposite direction to 10 newtons. Okay, so here I am writing net external force. F is equals to 25 is greater. So first I am writing 25 and here next I write 10. Since they are in opposite direction, minus 10. So F is equals to, I found 50 newtons. Okay, good. That is 15. Okay, next second part. Find out the total mass in the system, sigma m at. Luckily in this system, I found only two masses. Two masses. So m1 plus m2. That's it. That is 3 plus 2, 5 kg. That's it over. Next step there, straight away I write A is equals to, using my shortcut, F by sigma n. Okay. So here I write F is 15 by 5. That is equals to, simply I write A is equals to 3 meter per second square. Here actually I use 3 steps. Suppose if I practice more without using pen and paper, I say the answer. Directly by seeing the diagram. Okay, 25 minus 10. Okay, 15. 15 divided by 3 plus 2, 5. 15 by 5, 3. Directly without using pen and paper, I put the option. Okay, that much quickly we have to respond when we move to the objective exams. So now you understood my shortcut, Nana, what I explained here? Or still do you have any doubt? In IP, you want 2 marks for 4 marks question or 4 marks for 4 marks question, Mr. Manikanta? 4 marks. 4 marks means just by writing 3 steps there, do you expect 4 marks there for SAQ? You have to elaborate the question or not. That's why in IP, the elaborate method we have to use. That's why I explained the elaborated method here. Yes. Answer correct. You want, that's what I said. Here, if the answer is wrong, then obviously we strike off and we allot 0 now. But we are awarding 2 marks for 4 marks. Why? You did in a short way. If you write that one in the elaborated way, we put 4 marks. We are not giving 0. We are giving some marks to you. Now you understood, Mr. Manikanta? Yes, yes, yes. Okay, good. That's why don't use this method, shortcut methods in IP now, board exams. Okay, in board exam, go to the elaborated method. Which one, Mr. MS? .ms? The shortcut or this one? Example, what is that? Net force here. Suppose I'm asking you, Mr. .ms, this side I'm taking, this is 15 newtons. That side I'm taking 10 newtons. Now you only respond, not others, Mr. .ms. What is the net external force here? Black color, 2 forces, net external force. Yeah, exactly. You understood. That is net external force. And here, suppose this is 1 kg and that is 4 kg. What is the total mass in the system? Quickly. 1 kg, 5 kg. Very good. What is the acceleration? F by sigma m. Yeah. Then what is the doubt there, Mr. .ms? You only told all the 3 answers now. Right. Good. That's it. Okay. Good. So again, coming back, releasing the pass. Now we are releasing the pass. Oh, very. Well, you are my student, Nana. No need to say thanks. Okay. Right here. Okay. Here actually we have 2 questions, Nana. What is the acceleration? What is the tension? Okay. Out of these 2, look at, I can easily find the tension from the second equation. Why? Because straight away it is equals to T, whereas that is F minus T. So better I use the second equation. Okay, good. And it is actually a shortcut. Wow, what is the shortcut here, sir? Look the diagram here. Force is applied on the right side. Now go. Suppose there are many masses here. Okay, don't argue, sir. There are no masses. If many masses are there, n masses are there. Go to the last mass, nth mass. Okay, then the mass of nth one into acceleration is the tension in that connected string. Now you understood? In the same way here, 2 masses are connected. Yes, force is applied on the first mass. That's why don't see the first mass. Go to the second mass. Why? Because force is applied on it. So move to the second mass. Ammaya, no external force is there. Then look at the tension T is equals to straight away. T is equals to, I am writing here, from the equation 2. This is again IP derivation. I write here. T is equals to, that is M2A, and here that T is equals to M2 into acceleration. I already found here F by M1 plus M2. Here, Nana, F by M1 plus M2. Okay, it is the shortcut. Shortcut is up to here only. This is the shortcut. Shortcut part is over. Okay, good. So this is the shortcut for us. Then here, this is the tension, and again I highlight this one, take it as one equation. Okay, but I think this equation is not valid in all cases. Why, sir? Just to look at the beside example. Look at here. Force is applied and this is greater. It is greater means total system will try to move towards left or right, Nana? In this example, left or right? Left. Very good, very good, very good. So total system in this example tries to move towards leftwards. This is the acceleration. So when it is trying to move in this direction, exactly in opposite direction to the net force, the tension will be generated here. This is the direction of tension. Okay, here. Again, on the second mass, I draw the tension like this. So is it correct, Nana, the tension direction? Yes, yes. They should be, the two tension should be in opposite direction on the two masses. Yes. Now, anyone you select. Why? Because here there is no free mass, Nana, like in the theory what I explained. Here, luckily on the second mass, there is no second force. That's why we use the second equation as a shortcut. But here problem is on both the masses, external forces are there. We can't do anything. Any one free body diagram you have to select. So we need only tension. So we require only one equation. You only choose first mass 3 kg or 2 kg. I have to select anyone. One is second. Second means 2 kg mass. Okay. Yes, okay. Lakshmi Gayatri initially told that take 2 kg mass at all. Okay, according to Lakshmi Gayatri, here I am taking 2 kg mass free body diagram. Okay, I'm taking this as FBD. Okay, it is my FBD here. Right. It is FBD of second mass. That is 2 kg. Just only one FBD in numerical I'm using. Okay. Here the net force 25 minus T or T minus 25. Keep in mind it is moving towards left. 25 minus T. Very good. Why? Because it is moving towards left. Leftward force is more. So 25 minus T. That implies here coming to this one. Yeah. From FBD. F net is equals to, I'm taking here 25 minus T, and F net is equals to formula M into acceleration. The mass of this one, that is M2 into acceleration, is equals to 25 minus T, where M2 is equals to 2 kg. I write it as M2 here and I write there M1. Okay, M2 is 2 kg. So 2 into acceleration, already I got here 3. 2 into 3 equals to 25 minus t. Therefore, I am getting t is equals to 25 minus 6. That is equals to 19 newtons. Okay. Sir, please prove that it is 19 newtons, sir. Okay. What proof, Ranana, you require? Sir, here you said both the tensions are equal, na? If I take FBD1 also, I should get T is equals to 19 newtons, na? Yeah, good question, Mr. Student. Then prove, please, there also, sir. T is equals to 19 newtons. Then I believe that both the tensions are equal. Oh, right. You need some litmus test. Okay. Student is always student. Like men will be men. Okay. Uh, he is testing the master. Okay. Come to the litmus test. This time again, two forces are there. So from this FBD1, Nana, okay, um, it will come over. Right, good. Right. Okay, then Manikanta, here I have to write t minus 10 or 10 minus t. Ah, very good, very good. Why? Because it is moving backwards. I mean, say leftwards. Very good, very good. T minus 10. That's why I'm not deriving, just showing that. T minus 10 is equals to F net. F net is equals to M into A. Mass is M1. M1 is 3. 3 into acceleration is 3. That is 9. So T is equals to 10 plus 9. Wow, super, sir. So I believe that both the tensions are equal, sir. Now, good. Smart boy here. After deriving, he is saying that he believes. Okay. So all of you understood this concept, Nana? So we require two FBDs? No, I think one FBD is enough. Yes. That's why I'm removing the second FBD here. Yes, good. Now it is your turn. You have to solve one question here. Okay. I'm giving one question to you all. Are you ready? With all weapons, Diwali weapons. Yeah, ready. Right, good. Now, don't throw anyone on me. Just solve this example. And here I am taking the masses. Number 1, number 2, and number 3. Okay. Right. 3 masses here. This is suppose 2 kg. And it is suppose 1 kg. And it is suppose 4 kg. Okay. And here these two are connected with a string. And here those two are connected with another string. So keep in mind, here we use two strings. Okay, that's why surely I think you have to calculate the strings separately in the two strings, right? And look at the direction of force. Here for your convenience, just I'm taking only one force here. That is the force. And so suppose here this is say some 21 newtons. Okay. Will anybody quickly without using pen and paper say the acceleration and wow, good. Right. Acceleration. 2 answers. Next. Others. Good. 3, 4. Oh, Lakshmi Gayatri got wrong. 5, 6. Only 6 students are listening the class. Oh, here only there are 27 members in Zoom only. Now it is correct, Gayatri. What is this, Nana? In exam, we should not do the mistake, na? Yeah, good. Okay, anyway, we got around 7 answers. 7 members responded here. Okay, no problem. Here, I think using the shortcut, here I think I have to assume only one force is there, that to rightwards. That's why I have to take the acceleration towards right. There is no other go for me. I have to consider. Yes. And here that acceleration using the shortcut. A equals to, oh, he found the tension also. Good, good. This is the tension in first string or second string, Nanamo? Means this first string or second string? First one. Okay, okay, okay. Right. Then try to calculate the second one also. You both got different answers. Okay, okay. We'll check it, Nana. Here acceleration using, I'm using the shortcut. Why? Because preparing for objective. F external net divided by sigma m. F external, only one force is acting, that is 21. Oh, right. 21 by sigma m. 3 masses are there. So 4 plus 1 plus 2. M1 plus M2 plus M3. That is 21 by 4 plus 3 is 7. 7, this is, okay. Then Lakshmi Gayatri, here 2 students got the same answer, Nana. Once you check, I don't know who is correct. You are correct or they are correct. Anyway, I will check, no problem. 7 3s are. A is equals to 3 meter per second square. So here it is external force is towards right. So tension in the first string, I have to take in opposite direction to the external force like this. And of course, I have to take to action and reaction. Reaction is also there, opposite direction. Here I have to take it as in the first string T1 and T1. So already F is known there. So better I go to the first FBD. I take this one, FBD1. So I'm moving to from FBD1. All of you getting different answers now. But which is correct, I have to check here. Okay, almost we are getting that one. FBD1, it is moving towards right. So right is greater. 21 is greater. So 21 minus T1 is equals to, I have to write F net. MA. M 2 kg. So 2 into A. Whereas acceleration is 3. 2 into 3, that is equals to 6. So 21 minus T1 equals to 6. That implies I will get T1 taken to the left hand side, right hand side. T1 is equals to 21 minus 6. I think 15 is correct. 15 is correct and 18 is wrong and 7 is also wrong. Someone put 7. Yes, yes. 15 is correct now in the first string. So this is 15 newtons. Yes, yes, yes. Oh, second one is, yeah, second one is correct, Mr. Amok. You are right. Second string, someone put here 9. That is wrong, I think. Who is Akhil? Even Manikanta also put it is 9. It is not 9, I think, Nano. Yeah. Are Manikanta? Wrong. So look at the second string, Nana. Here, second mass here, it tries to move towards right. Means here T1 on the second mass should be greater. So it tries to move towards forward. And here immediately tension will act in opposite direction here. Action and reaction. So these two must be T2 and T2. Okay. So here if I check, those T2 are acting on 1 kg and 4 kg, but I prefer 4 kg mass. Why? Because here there is only one force. If I see the FBD here, that's why instead of going to 1 kg mass, I prefer 4 kg mass. 4 kg mass, I take it as FBD2. Okay, in the 4 kg mass, I found only one force is there, and that is F net is only T2. T2 is equals to F net. F net formula is mass into acceleration. Mass is 4 kg into acceleration. That implies, I write here, T2 is equals to 4 into acceleration is 3. That is equals to 12 newtons, not 18 newtons. No? Okay. I don't know where you did the mistake, Mr. Manikanta. 18 and 24 you are putting there. Why? Why you got 18 and 24? Where is the Mr. How much acceleration you got there? Mani Babu? Babu Mani, Babu Bangaram. Babu Bangaram, please respond. I forgot the formula. I got T2 and then. Babu Bangaram, what is this? Okay, okay, no problem. Right. Okay, now you understood the two things and try to correct them now. Next time, don't do the mistake, Mr. Manikanta. Right, right, no problem, no problem. It's not an issue. Okay, here, this is the way how to use the free body diagram and how to calculate F net and acceleration. Okay, better we stop here, Nana. Okay, if you have any doubts, you can ask. In all the examples, what we saw, no doubts. Okay, right. So, do you want any pages here? Or straight away, shall I stop the class? Yes, you want the pages. Okay. Number 1. Number 2. And number 3. Okay, ma'am. Welcome. Okay. Okay, Nana. Bye, everyone. Have a nice Sunday. Enjoy. Okay, okay. Happy weekend to you also.